Dani, por la invitación. Es un placer volver a Santander y participar en este workshop. Y creo que yo también voy a pasar al inglés porque una sola vez intenté dar una charla en italiano y fue un desastre entre francés, inglés y inglés. Así que creo que en castellano va a ser igual.
Con mano.
Empezarlo así. Y nada, justo antes de empezar, bueno, nada, el curso va a ser bastante sencillo. Quería contaros un poco lo que sé sobre este OLED compresible a densidad variable, resultados viejos, unos un poco más recientes, y nada, y contaros un poco lo que me interese. So, let's start with the short introduction. So the system of equations we are interested in is the incompressible Euler system with variable density. So we have essentially three unknowns: rho, which is the density of the fluid, u, which is the velocity field, and p, which is the pressure. And we have seen a lot about, and you already know probably the form of the system. So we have an equation for the velocity field u, which is, as we have seen in the course of Diego, the Newton's law applied to the fluid particle, let me say. And of course here there is the mass, actually the mass per unit volume, which is rho. And the mass evolves according to the principle of conservation of mass, which is pure transport by u, and u is divergence free. Okay, so we will set these equations in a very simple domain. So, in R plus for the time variable times RD and D, which can be greater or equal to D. Okay, so I will immediately restrict the attention. I will immediately do some simplifications. So we take f equal to 0. It will play no essential role in our results. And I will also take most of the time d equal to 2, because we will see that this does not make a huge difference in the theory. And I will assume always absence of vacuum. So I will always assume that there are positive constants, rho star and rho upper stars, which bounds my initial density. And actually these bounds, at least if the flow is regular enough, are propagated by the flow, and so for any time t for which the solution exists, we have the same bounds for the density also at later times. So in particular, if we start with the initial density, which is 1, the density remains constant, and the system reduces to the incompressible Euler that we all know. And just let me recall a couple of facts just to make a comparison with the mathematical theory of the density-dependent case. So, okay, this is the incompressible, the classical incompressible Euler, for which we all know that if we define the vorticity as the two-dimensional curve of the velocity field, then omega, now I mean 2 dimensions, omega is simply transported by u. Okay, and in particular, this simple transport equation is at the basis of global workhorseness. In Sobolev spaces, Euler spaces, and so on. So which are embedded in C01, so in the space of globally reached functions. Secondly, we know that we can solve globally in time also for a less regular initial data, and for instance, we have the so-called Yurovich theory. So we know that if we take an initial vorticity, which is say L1 cap L infinity, then there exists a unique global in time weak solution for which omega is L infinity in time, L1 cap L infinity. Okay. And in particular, as a byproduct, we can propagate the structure of vortex patches. So if we start with an initial vorticity, which is the characteristic function of the bounded domain D0 in R2, then there exists a unique solution omega. The velocity field corresponding to omega is log Lipschitz, and so we can define a unique flow, and actually the structure of vortex patch is propagated because at any time t, the vorticity at time t is the characteristic function of the domain dt, which is just the propagation of d0 by the flow associated with it. Okay. Actually, so as I said, all these results are based on the simple structure of the vorticity equation. If we now look for a vorticity equation for the density dependent case, so what we do, recall that I have taken f equal to 0, and we have assumed absence of vacuum, so we can divide the equations, the momentum equation by rho and take the curl, and we discover that omega solves a transport equation by u, because of course there is the same cancellation as in the classical case, but there is an additional term which appears, which depends both on the density variations and on the pressure. Okay, so here gradient perp is just the gradient turned over P over 2, divided P over 2. So in particular, we notice three main differences. So first of all, we cannot avoid the presence of the pressure in the equation, so we will have to analyze it. Actually, this is just a technical point. There is no huge difficulty in it. But the second point that we see is that there is no hope to propagate. So first of all, so consequences. So as I said, the pressure cannot be eliminated, and the pressure, so I said it's just a technical matter, but as in the homogeneous case, the pressure will be quadratic in the velocity field. Even worse, the gradient of rho grows exponentially with respect to the Lipschitz norm of u. So in particular, we see that this term is dramatic, has dramatic consequences for the global well-posedness theory. So all the results, most of the results are, actually almost all the results are just local in time. Local in time well-posedness. The second point is that...
in the same spaces, right?
In the same spaces, exactly. I will give a statement for a more general class, but in a while. But yes, in the same spaces, as soon as you have the embedding in the global Lipschitz functions, you can solve. On the other hand, because of this term, it is not clear that you can, in general, you cannot propagate the vortex patch structure. You have formation of vorticity, and even worse, so no vortex patches. But even worse, also Jurovich theory fails. In the sense that if we want to impose only initial vorticity in L infinity, then in order to propagate the L infinity norm, we need an L infinity norm for the gradient of rho, which requires u to be Lipschitz. So we automatically go up to the Lipschitz theory. We cannot stay in the Jurovich class. Okay. Okay, after these preliminaries, I will speak about classical well-posedness result, precisely in those spaces and generalizations. So there is so there are several results in different contexts. So to the best of my knowledge, the first Wilbusness result was due to Beirauda Vega, and the Valli. These in C1 alpha spaces in a bounded domain. Then in 2006, Danshen considered the HS framework. And also considered the implicit limit in absence of boundaries. And in 2010, again, Danshen proved Wilbusness in Bezov spaces, DS, PR, which are embedded in C01. So, and this happens whenever S is larger than 1 plus D over P, or S is equal to the critical index, but at the same time, R is equal to 1. Okay, so probably I should not recall the definition of Bezov spaces here. Just remember that S is the index of regularity, P the integrability. Okay, so and this is the classical condition for so-called inclusions. In the class of Bezov spaces, you can recover also the endpoint index. Just a remark that the spaces HS are characterized as special Bezov spaces, where both B and R are equal to 2. And the other classes, so C0 alpha, are characterized as B alpha infinity infinity. And actually this is true also for higher regularity spaces, but always for non-integer regularity indices. Okay. So this result of Danshen was proven for any P in between 1 and plus infinity. So I would like just to give a statement proved in collaboration with Danshen in 2011, where we considered the endpoint case, and in particular by which we could reach the endpoint space V1 infinity infinity, which is the largest space in this class of inclusions. So the theorem is the following. So we have either S larger than 1 or S equal to R equal to 1. As before, we assume absence of vacuum. And we take an initial datum U0, which is L2, and BS infinity R, of course of divergence 0. And an initial density, which is BS infinity R. Okay. And then we can prove local and time existence. So there exists a positive time and a unique, well-posedness, local well-posedness, not just existence. And a unique solution on 0t times RD. Now I go back to the general situation. Okay, such that of course we gain continuity in time in the respective Bezov class. Well, let me write this. And we propagate the L infinity norms for the density. So U is continuous, and it is C1 in time with values in L2. And the pressure is continuous in the Bezov class intersection. Okay, in addition, we have a continuation criterion, which is a similar spirit to the weak AMAED one. So in particular, if T star denotes the left span, and it is finite, then we know that the integral up to time T star of gradient of u in L infinity plus a lower order norm of the pressure function, of the gradient of the pressure function, has to blow. Okay. So some remarks about this statement. There are just a couple of remarks. So first of all, so one may wonder why an L2 condition on the velocity field. So actually we need some integrability in order to reconstruct the pressure gradient, in order to solve its elliptic equation. And the L2 space is very much convenient. However, we can also consider infinite energy solutions. So in particular, the assumption U0 and L2 may be replaced by U0 in some LP and gradient of U0 in some LQ, where P has to be larger than 2 and Q larger than 2, and such that 1 plus P, 1 over P plus 1 over Q is larger than 1. Okay.
Sorry. So the density does not play any role?
No, in the continuation criterion, no. No, you can forget about it, because essentially rho is just the equation for rho is just linear in U. So in fact the only information that you need in order to continue the solution is hidden there.
If that's controlled, then you control the gradient.
Exactly. Okay. So, and actually how to do that, we just got in the vorticity. For the vorticity we have a transport equation, so actually the LQ integrability can be propagated. The second remark is that the presence of the pressure term here is not natural in this continuation criterion, and actually it was removed. Continuation criterion can be removed, and this was done in a paper by Lee and Shin in 2000. So one really have a continuation criterion like the Milcato-Maida one. Of course, the gradient of U in L infinity can be replaced by the norm of the vorticity in L infinity whenever you are in a subcritical case, so S larger than 1. Okay. So just a few words about the analysis of the pressure. So proof that in fact just pressure. The proof is nothing more than transport estimates in Basel spaces. The only new point is the analysis of the pressure. So in this context, the pressure satisfies the following elliptic equation. So it's the same equation as in the homogeneous case, but now there is the presence of a variable coefficient in front of the Laplacian on the right hand side. And actually, one would like to find to solve for the pressure in a way which is independent of the density function, and you can do this just in an L2 framework. So if you try to solve in LP for P different than 2, then constraints over the density appear. I think so. The P's that you can reach will depend on these L infinity bounds, rho star and rho star. And actually, you cannot move too far from 2 in any way. So we take the L2 framework as effect, and we work in this framework. So this is why we impose the conditions in order to have U scalar gradient of U in L2. So in order to solve for the pressure in N2, we need this to be N2. So this is why that is assumptions or this one. Okay, so of course the N2 normal for the gradient of the pressure is not enough, so we need to propagate the higher regularity in order to employ this on the right hand side of the equation for you. And how to do that? Actually, so for higher order norms, we compute the derivatives and we find an equation for Laplacian of pi. So we propagate higher order norms for the Laplacian of pi. And so we find this minus Laplacian of pi will be plus or minus, and remember the sign, log rho times gradient of pi plus rho gradient of u, gradient of u. Okay, and so if we want to estimate the pressure in some base of norm, we can split in low and high frequencies. And actually this can be controlled by the N2 norm, which controls the low frequencies, plus a lower order norm of the Laplacian. Okay, so we need to look for estimates for the Laplacian of pi in lower order regularity, and we see that the gradient of pi, which appears on the right, is actually a lower order term, so it can be absorbed by an interpolation argument on the right hand side of the estimates.
So what's the regularity of rho here?
Of rho, it's Bs. So this term is Bs minus 1. There is just one point which I mentioned right now. So this is the general strategy. And so we can close the estimates in the classical way, inserting these estimates in the equation for u and then applying transport estimates for u and rho. There is just one delicate point which concerns the endpoint case s equal to 1, because so when s equal to 1, we have said that we work in the base of space B0 infinity 1, but B0 infinity 1 is not an algebra. So actually the analysis of the product terms is more involved, is more delicate. And actually so in particular we have three kind of terms that are nonlinear and which we need to control in B0 infinity 1. The first term appears in the equation for the vorticity, and it is this term. The second one is precisely gradient of log rho, scalar gradient of pi, and the third one is this one, gradient of u, gradient of u, for which we cannot apply the algebra estimates. So the solution for this actually is simple, because we apply a paraproduct decomposition method, and by this there is just one term which is out of control, which is the term where the frequencies of both terms are mixed and are of the same order. So we have the first term, second one, plus the second one first, and then we have the remainder. Okay, and the remainder, so the problem in this estimate, in the fact that this space is not an algebra, appears precisely in the remainder. The basic point for the first and the third is that we can factorize one derivative. And so this is nothing but the kernel of 1 over rho gradient of pi. And this one is just the divergence of u gradient of u. And so in analyzing this term, we can factorize one derivative. Of course, we have to estimate this term in a space of higher regularity with one derivative more in B1, but both 1 over rho and u are B1, so we can close the estimates and control these terms. As for this one, we cannot really do that because we cannot factorize derivatives. There is no commutation property. but what says us is that actually this term is more regular. So we in algebra estimates we would like to estimate the first term in B0 and the second one in B0. And I said that this has to be treated by interpolation. This estimate is not true, but actually it becomes true if here we put something more. And still 1/2 is lower than 1 and we can apply the interpolation. So we exploit the fact that the remainder is more regular and that we can play, we have a little bit of regularity in order to play with and to absorb then the bad term on the left. Okay, so this is more or less how the a priori estimates work. And now, and then the rest of the argument actually is classical. As I said, we cannot hope to, at least for the moment, we do not know whether the solution is global or not, but we can give a lower bound for the lifespan. And so we have this theorem. So under the assumptions of the theorem, there is a constant which depends just on the L infinity bounds of the density, such that the lifespan of the solution can be bounded from below by C over the norm of U0 times the logarithm of the logarithm of here there is a constant of gradient of rho 0 in B0. So why this criterion? Why this is interesting? Well, because they said that the system is essentially a coupling of transport equations. So and in getting estimates, we apply just the transport estimates. And the theory of transport equations, nonlinear transport equations, would give just a lower bound of the kind C over the norm of the data. So the norm of the data are both rho 0 and U0 in the functional space we are considering. Okay, of course, this quantity remains bounded whenever rho 0 tends to 1. But we know that this is specific of space dimension 2. This is fundamental. We know that in two space dimensions, the incompressible Euler are globally well posed, so we wanted a lower bound which was reminiscent of that. So for which, whenever sending rho 0 to 1, we recovered a global entire result. And this estimate actually is in accordance with that, because as soon as this vanishes, the time goes to infinity. A couple of words about the proof of this. So there is one ingredient and no more. And it is, so the basic ingredient is to estimate. So you see that here I worked with S equal to 1. So working in a critical regularity framework is the key. So working with the vorticity in B0 infinity 1 is important, because for linear transport equations, let me say even with divergence-free vector field, in Bezov spaces with the index of regularity 0, one can rely on improved transport estimates. And this was proved by Vishik in 1998, and then with a different proof by Midi and Kerani in 2008. Yes. So these improved transport estimates work in this way. So we know that in order to propagate regularity, base of regularity for linear transport equations, we have a growth which is exponential in the Lipschitz norm of the velocity field. Now, if we work in a base of spaces with the regularity index 0, this growth is no more exponential. We still have a growth, so we are not estimating the function in NP. So we still have a growth, but it is linear in the Lipschitz norm of V. More precisely, the norm of F in B0 PR, so here PR can be whatever, are controlled by the same norm of the initial datum plus the L1 norm of the force. And here the growth is, as I said, linear, so we have a term which is gradient of V and infinity. 1 plus the L1 and infinity norm of gradient of V. Okay, and so repeating a priori estimates for our problem with these improved transport estimates for the vorticity yields in turn to the result, to the right lower bound for the lifespan. Okay. Okay, so
this is in any dimension, right?
this in all dimensions, right? But here, in order to have this lower bound, we really need to be in dimension 2 because there is no stretching term. If we have the stretching term, we have we would have in this G a term of the form omega gradient of U, which is quadratic in the solution, and which is not small when rho is small. We have no rho in front of this. Whereas the pressure, it is true that the pressure is quadratic, but we have a gradient of rho in front, which in the end produces a small gradient of rho 0 in front. And this is the term which gives in turn this graph. Sí.
Vale. Ok, si cambias los espacios de peso a espacios HS,
Okay, so
¿sigue siendo el log-log? O sea, quiero decir,
you want to put the higher regularity norms here.
Which norms are you talking about, Rafael?
Some HS.
HS.
So
Instead
they
of
are-
B1 infinity 1,
I would say that they are larger than those, so you have, so you go in the right directions, right? So here you can bound this from below by C over the norm in HS, log of 1 over gradient of rho in HS, if I'm not wrong, right? And are you convinced? No. I would say, so coming back to your question, I would say that the log growth will remain.
my point is because this B, so listen, working with vorticity in B0 infinity 1 is important. Okay, because of this. Fine. So in order to want to do the theorem with the HS, you do this, and then you use the embedding of the spaces, right?
Mm-hmm.
So my question is whether you can try to directly prove it in HS.
So I'm not sure 100% that the log remains. I would expect a yes, because this should be something intrinsic of the equation. But let me add a remark to this proof. So here we used the local well-posedness result in these endpoint spaces. Actually, what is really important is not really to have an existence theory, local well-posedness in the endpoint space, B0 infinity 1. What is really important is to have local existence in a high regularity space plus continuation criterion. And this norm of the vorticity just controls the norm appearing in the continuation criterion. Okay, when doing that, maybe there are higher order norms which appear here. So here there is not just the D0 norm of the force, it will be HS. And then for that you may have more complicated estimates. So actually here you can, because of this procedure, you may find a different function here, which is still explodes when gradient of rho 0 becomes small, but which is more complicated.
Okay.
So that argument was employed in a work with Cobb, but for a different system. And in fact, we found a triple logarithmic there. But I suspect that it's really tied to the system and not really to the kind of norms we employ. But I have not a proof for that. As third argument, third chapter, sorry, I would like to speak about global existence results. Related to our system. So I essentially know a couple of them, but okay, let me make this precise. So the first result I know is by Chen, Wei, Ping Zhang, and Zifeng Zhang, which is an active preprint of 2023, and as far as I could check, it is still not published, but this is global existence by, in fact, asymptotic stability of shear flows close to Earth. So the system is set in the same space as Rafa did for his system. So this is the space domain in R2. Okay, so those authors expand the solution close to wet flow. So we have learned by Daniel. So we have a static density rho bar equal to 1 and the V bar equal to Y0. And so the authors study the equations for the perturbations, which now I call the perturbation rho and u accordingly to the previous system. So the rho and u satisfy, actually they instead of rho they use the variable a, which is 1 over rho minus 1. Okay, so they recast the system in this form, that a plus u scalar variant of a plus y dx a equal to 0. And for u, we have a density dependent Euler with additional terms. There is one what's appearing like that, and there is the pressure term which is recasted in this way. And of course, u is the regency. Okay, and the theorem is the following. I put it for, I hope it is interesting for you. So the theorem is really a global existence close to this special static profile. So you take a beta 0 small, okay, and you take initial data which are in this Gevrey type space beta 0 1 half, where the space is G lambda S, for S in between 0 and 1, and for lambda positive, are defined in this way. We have periodicity mix, so we sum over k, we integrate over R, and we take the exponential of 2 lambda 1 plus k squared plus c squared S over 2. So lambda is a sort of radius, and S is the exponent of this exponential, of the function appearing in the exponential function. Okay, so in addition, this delta have to be small, very small, in this space. And in addition, omega 0 has to be of 0 integral. And with finite first moment. And then there exists a unique global solution on R plus times omega with a small norm, of course, and actually polynomial decay in time. Okay.
So there's implicit then.
Yes, in this context, indeed. They do global existence in this context. Precisely. Yes. And they mentioned that there's a question to obtain the same result in t times minus 1, 1 with suitable boundary conditions. So with no penetration boundary conditions. But they are feeling that they have troubles with the pressure term. So for the moment they are not able to get this. So the domain is still is unbounded on the y direction. Okay. And the second result is a result with Marco. So but for a modified system. So actually we cheated a bit and we introduced the damping in the momentum equation. So there is this parameter alpha positive, and there is a rho u equal to 0, and actually we introduce a power gamma where gamma can be either 0 or 1. So the gamma equal to 1, as far as I understand, is the most physical case, but it is also the easiest one. So to complicate a little bit, we treated also the case gamma equal to 0. Although I think it should be less physical. And divergence of u equal to 0. So just to, and we worked still in absence of boundaries, so in the full RB. Okay. And okay, just to mention some related literature. Of course, we are not the first one to introduce the damping in the momentum equation. So I would like to mention related results. So the first class of results concerning the compressible layer. So there is a first paper by Sideris, Tomasis, and Wang, if I remember correctly, of 2003. Who proved the global existence for compressible layer with damping. And now there is an active research line initiated by a paper by Bouchard and Zoua related to control theory. And now so this is a paper from 2015, if I'm not wrong. And now there are works by Krimbarat and Danshen. So so some papers in 2022 and 2023, because actually these systems enter into the context of partially dissipative hyperbolic system. So of course in the compressible context, the pressure term is a given function of rho, and so the interest is that so you have dissipation but which acts only in one component of your hyperbolic system, and so the work is trying to find a damping mode which actually combines the damped variable and the other unknown which is not damped in order to get decay, to improve the decay that you expect. So there is some structure behind the hyperbolic systems which can be treated, which actually reminds some conditions which appear in control theory. So this is why actually these works are pretty much related to the one by Charla as well. Okay, and in the context of incompressible Euler without density variations, let me mention a result by Angel Castro, Diego, and Daniel. Of 2019. So please correct me if I'm wrong. You solved the damped Bussinesq equation in this domain 3 times minus 1 1 with non-penetration boundary conditions and still close to some shear flow. Am I wrong, or just for any? Close to stratified profiles. Right. Thank you very much. Yeah. So there were an additional question. So the nonlinearity didn't come into play in front of the acceleration term, but it was the buoyancy force on the right-hand side. And in the context of IPM, instead there is a recent work by Bianchini, Krimbarat, and the Paipu, who exploited this idea of damped modes in order to improve a previous result by Gindi. Of 2017, maybe, I don't know. So about the IBM equations. And also in that context, actually, the rho, so the momentum equation was somehow simplified, and you didn't have a non-homogeneity appearing in front of the acceleration term, but just as a buoyancy on the right-hand side. Okay, so I would like to state essentially two results for this for this case. So what we are able to prove is global existence for small data for our non-homogeneous Euler. So the first theorem is the following, and maybe I will stop with it. So in any space dimension, and for gamma equal to 1, so we have a constant which only depends on the n infinity bounds for the density, and there exists another constant which only depends on the density, on the space dimension, such that the following holds. So we take initial data ρ0 and u0. For simplicity, let me consider the endpoint case. So I take u0 in L2 cap b0 infinity r, where S and R have to satisfy the same constraints as before, but actually this is not important. We could work even for different p's. And we take ρ0 in bs infinity r. So, of course, for ρ0 we have these bounds. So the assumption is as in the previous theorem. Okay, and then we have the smallest condition. So if 1 over alpha, the norm of u0 will be 1 infinity 1, and then there is an ugly function, it's an exponent of some norms of both rho 0 minus 1 and of u0. So if this quantity is small enough, then there exists a unique global in-time solution to the incompressible order. And actually we also have a decay. So u, so exponential of alpha t, u of t in the higher base of norm, and plus a double exponential growth, still an exponential growth, but with 2 alpha instead of alpha for the gradient of the pressure. So this is bounded. And sorry, there is no eta in this condition, but eta is an exponent which appears here inside, but it's not interesting. Okay, so essentially this theorem tells us that either we have a small initial data or arbitrary initial data, but the damping has to be very large in order to get the global existence. We have a similar results also for gamma equal to 1, also for gamma equal to 0, but here the nonlinear condition is much more involved. But still the moral is the same, either small data and the I forgot, I have to check, but I think that the smallness in the case gamma equal to 0 has to be also in the density function, so rho 0 minus 1. Okay, or arbitrary initial data but large damping. And the second result I would like to present is instead related to the case d equal to 2, but this we are able to state it only for gamma equal to 1. And this result tells us that if only the variations of the density are small enough, then we have global existence, which is moral compared to the previous theorem. So maybe I conclude with the statement, and then I will continue tomorrow with some elements of the proof, and then.
So if in this inequality, if you take density to 1, you get the global existence for all the initial data, or no?
In all space dimensions, for gamma equal to 1, no, because this degenerates, but we still have this condition. So we still need some smallness or largeness parameter. No. Unfortunately. Okay, so the b equal to 2, gamma equal to 1. So there is this kappa as before, such that, so if norm of rho 0 minus 1 will be 1 infinity 1 plus rho 0 minus 1 be 1 infinity 1 to the power eta. This eta is the same as before, but now we have a precise expression. Well, it is explicit because the dimension is fixed. Actually, we know that eta has to be larger than 5, but we can take it arbitrarily close to 5 as we want. Okay, so this times a function which I call just phi k because it is there where the constant k appears, which depends only on u0. So this product must be small enough. Then there exists a unique global solution with the same decay estimates for u and the gravity of okay, so just to comment that the smallness conditions are rest only on the low regularity norms, and precisely the interest for the equal to 2 was to remove the smallness of the initial velocity and just to put the smallness condition for the density. We opened to be more general, but actually we still need some smallness. And okay, the plan for tomorrow is to just give some ideas of the proof and then to switch to consider vortex patches problem in generalization for the density dependent case. So I stop here. Thank you very much for your attention.
¿Alguna pregunta o comentario?
Is there global existence for large initial data, or
For the damped
no. For the problem without damping?
No.
No?
No, it's not known for the moment.
It's not known, but
No.
but that, I know it's not known. I'm asking you. I'm asking you. And there's they're taping you.
So I have to pay attention to what I say. So I trust in physics and I say that the density cannot destroy everything, so I pretty much confident that the result for the homogeneous case should be true also for the density case. But this is just a hope, it's not...
Okay, are there numerics done?
I have no numerics for
there's
no
no evidence.
It's a very, very interesting question, yeah.
So there's no evidence, there are no...
No, it's just my hope, very naive hope.
Okay.
Yeah. So I should be less smiling than
Very interesting.
So, any other question or comment? Just one stupid question. Can you repeat what is the difference between these two theories in the case gamma equal to 1? Because I don't...
So in the case gamma equal to 1,
yes.
Right? So the fact is that here we work in any space dimension, and so the smallness of the density close to 1 is not enough, of course, because the Euler in any space dimension, so we have seen that it develops similarity, so the damping is not enough to produce global existence. You need also smallness of the initial data, either smallness of 0 or large damping. Here instead, so here of course the alpha is coming into play also in this function, but in the context, in the second theorem we restrict to the case d equal to 2, and the smallest condition only rests on the size of the initial density.
Only in raw.
Exactly. So of course, so there are some complications, but if you forget about those, and if the density variations are small enough, then you get problems.
So there is no smallest condition in this phi function?
No, actually no.
Okay. So
No, it is a function of this norm. It's actually another exponential, not that far from this function here, but really the leading part is.
okay, so thank you. No question, no comment? So thanks Francesco again.
Very nice.
Y continuamos mañana, 11:30. Entonces.
Espero haber terminado.